Welcome back, everybody. I hope you're doing fine and you enjoyed the first few weeks of this course. So in the current week, we are going to be talking about interprocedural program analysis. And here I'm also going to be using a couple of slides from my dear colleague, Uday Ketka. To just put this into context, so we already discussed flow insensitive analysis and type systems in the beginning. And then we discussed how to use lattices and fixed points to actually define so-called intra-procedural flow-sensitive analysis that operate on a single procedure using the monotone framework. We discussed a couple of extensions, such as widening and narrowing that can be used to actually speed up the computation. And then in the last couple of weeks, we talked about call graph construction and all these nice algorithms that are supported, for instance, in the Spark framework. And we also talked extensively about pointer analysis and must analysis, may analysis, strong updates, how that is all connected. And now we are going to be putting all of this together to be conducting interprocedural data flow analysis, and in particular also interprocedural flow sensitive analysis. That's what I'm going to be talking about this week. And first I will be talking about some challenges that this involves. And then in the next few weeks, we are going to be talking about different ways in which these challenges can actually be addressed. So today we will cover general concepts of interprocedural program analysis. We will be talking about a very important concept, probably the most important concept in this space, which is called context sensitivity. But then in the end, I will also briefly be talking about some practical considerations. So there are also a number of challenges that are largely ignored in theory, but that you do encounter in practice when you're analyzing actual real-world programs. And I would like you to be at least aware of them. So I will explain what these challenges are. So talking about interprocedural data flow analysis, I guess it should be clear that this extends the scope of data flow analysis across procedure boundaries, right? And it does this in two different ways. So you can basically think of this as data flows in two different directions. So first of all, if the analysis encounters a procedure call while it's analyzing a current procedure, then it has to incorporate the effects of these calls into the caller procedure, right? So looking at a method call, you basically want to figure out what is this call all about, what's going on there, and what does this mean for the procedure I'm currently analyzing. The other way around, we also have to take so-called calling contexts into account in the callee procedures. I'll still be talking about that extensively on the next few slides. And there are several approaches to dealing with this. So there are a couple of generic approaches, or what I would also call conceptual frameworks. And in particular, there's the so-called call strings approach that we will be covering in depth, and also the so-called functional approach. And these have existed since the 60s, but they have been perfected quite a bit since. And then there are very problem-specific instantiations of this. So here we're talking about alias analysis, points to analysis, also other kinds of analysis such as partial redundancy elimination or constant propagation. So these are basically instantiations of these frameworks. And at the same time, these are also very often, so at least the ones on the bottom here and the last line are often client analysis, so-called client analysis to these more basic analysis such as alias analysis and points to analysis. So let us talk a little bit more about these effects that need to be incorporated. So here we are looking at a relatively simple program structure. So we have a function R in the middle represented by the starting node of R, and then some data flow that is represented by this function FR that ends up at some exit node ER here, okay? And then we also have some functions S and T that call into R, and they have some data flows on their own. So for instance, when you start here analyzing S, you end up with some data flow fact X here at this call site CI that calls R. Okay. Similarly, here you have a data flow item Y. And then we also have additional data flows down here that I will get to in a minute. And so if you look at this, there are so-called inherited and synthesized data flows. So the inherited ones are the ones that go from the callers here to the callee. Okay, so X and Y would be so-called inherited data flows that come from this and this call set respectively. Then also we have synthesized data flows. These are the ones here at the bottom. So basically we get X or Y as an input here, and then we apply FR, which gives us FR of X resulting in X prime and FR of Y resulting in Y prime. And then these data flows respectively are being propagated as synthesized data flows back into the respective calling contexts. Okay, so this is a synthesized flow that basically tells you at this program point here what is actually the effect of having called procedure R at this particular call site here. And there are a number of examples that you could use for these different kinds of data flows. So in general, if you're talking about inherited data flows, this is about answering questions, for instance, about formal parameters of the current method that you're analyzing, but also about global variables that are in scope everywhere within the program. So this could be information such as which variables, for instance, carry constant values at the moment, which variables are currently aliased with one another, or also which locations can a pointer variable, for instance, point to. This is something that depends a lot on the past computation that has already happened in the program, and that can be beneficial to know when you're analyzing the current procedure, right? So this is why this kind of information is always being passed down into the callee as inherited information. When we're talking about synthesized data flow information, this is more about answering questions about the effects or side effects, you can also say, of a procedure call. So for instance, you might wish to know which variables are defined or used or called by a given procedure, or what state changes are created, for instance, by calling a certain procedure. And this can be with respect to local, global, or formal parameter variables. Also, an important side note, most of the above questions, they can have a may or must qualifier, right? So that means you can have inherited must information, for instance, a must constant information, or may constant information. I'm not sure if that makes sense in that particular combination, but you could think of something like that. Yeah, in general, you can combine this as you please. And in the previous lecture, we already talked about how this can be achieved using must alias analysis and strong updates, for instance. Then the next step is that we want to model these synthesized and inherited data flows using one uniform data structure. And in this case, the data structure is called the interprocedural control flow graph, or commonly also denoted by ICFG. In some papers, you will also find the notion program supergraph that typically refers to the very same data structure. And in order to build such an ICFG, let's look at what we already have. So we are assuming that we already have individual control flow graphs for different procedures. So here we have a control flow graph for procedure main that does some numeric computation and calls a procedure P and then ends. Okay. We also have a procedure P, which is called here, that calls Q and then ends. And this is procedure Q, which actually has an if then else. And depending on which branch is taken, it does some different computations or maybe also not. And then it may end up calling P again here. Okay. So that's just an example of a number of intra-procedural control flow graphs that we could have independently for different procedures of a given program. Then the other thing we have is a call graph. At least that's what we assume here. And you have seen a number of call graph construction algorithms. So this can be a rather crude but imprecise CHA-based call graph. It could be one generated by an Anderson-style pointer analysis. Right now, we don't care. We only care that we have a call graph that that gives us information about the caller-callee relationship. So by looking at this call graph, we now know that there is a call site in main that calls P. P can call Q, and Q can actually call P. And in this representation, we actually even have a multi-graph. So this would even encode that there are different call sites into P. So we would actually even distinguish this call site here from that one using the call graph. Okay, and that's actually typically the case, right? So if you look at call graphs as they're implemented in Suite, for instance, or in Spark, they have granularity at the call site level. So you know at least at which call site which procedures can be called. Now, there's one little trick that's often played in the literature, and that is that these previous call nodes that I had in the graph, in these individual control flow graphs, that they're frequently being split up into individual call and return sites. You already saw that in the initial slides. So this is just to make this a bit more readable and to make it more easy to reason about this. So in Suite, for instance, we only do this conceptually, not actually in the implementation. You don't really need to do it in the implementation, but sometimes it makes reasoning a bit simpler. But basically the idea is that here you call into some procedure P, and then when you return, you don't get back to this node, you rather get back to this node, and similarly down here. And now you take the call graph that we have computed, and you take these individual control flow graphs, and you simply overlay them, right? So you could think of it also as a cross product of these two data structures, and that's basically what you get. So according to the call graph, we know that this procedure call to P actually does go to procedure P here. This is now a very simple determination, right? There's no virtual method call involved here anywhere in this program. So these connections are actually straightforward, right? And now I've colored these edges to denote that this is one call to P, and then this is the corresponding return edge returning out of P back into main, right? And so with different colored edges in these other cases, obviously in the actual call graph or also ICFG, they are not colored. But of course, they are sort of labeled, right? Because you know where they originate and where they end. So you certainly know which call sites and which procedures are involved. But what's interesting now is that what I've done here is I've really simply, basically taken a union of these edges that we had in the call graph and the ones that we had in the individual control flow graphs. And I've just plainly put this together, but this is generating some problems now if you carefully think about it, because in this combined graph, you can now actually have certain paths that are actually not really valid, that are unrealizable at runtime. Let me show you some examples. So first of all, what you see here now in blue, that is actually a valid path, okay? Because this is a path that starts at the beginning of the main method, so that's already good. It's calling P. We start executing P. We are calling Q. We start executing Q. And now from the end of Q, we return back into P as we're supposed to. And now here we stop. Okay, so you could argue that this is not a valid run of the corresponding program because we're actually stopping here prematurely. But most programs, they can be preempted early, right? Or the execution can be preempted. So you never know whether a program will execute to completion. So this is actually a perfectly valuable path in most, situations that you will actually consider. Um, and we actually also know that this is true by considering a call stack, right? So I told you when we go here into P and then into Q, we're actually considering that, when we return here from Q, we have to return back into P. And we know this because in our mind, we're basically keeping track of a call stack, right? So we know what were the previous procedures that were called. And so this then gives us a notion of a so-called realizable path. So a realizable path is one where the appropriate procedure calls match up inversely with the matching returns that you have according to the call stack. Now, given that notion, we can also describe what an unrealizable path would look like. So looking at this again, for instance, we can look at the possibility of extending this path here along this edge, or maybe also along this edge, okay? And looking at this part here of the call stack, we can see that this is not actually correct. That would be unsound, right? Because well, it would actually lead us to an imprecise result, let's say, right? So just to clarify, because here we have the situation that we are in procedure P, and looking at the bottom of the call stack, we know that we should now be returning to main because this is where P was called. It wasn't called from anywhere else. And so it makes no sense to return to Q like you see here. Okay. So any of these two paths, the rose one and the green one, that would be unrealizable. So this is also called an interprocedurally invalid path. And the question is now, how do you recognize such invalid paths? And in general, we are interested for one in actually finding such paths that originate from one procedure, right? So that have a call, an incoming call from a procedure such as T, for instance, but then return to another procedure, right? So we have non-matching returns that do not match any corresponding calls. Another way of thinking about this is such a staircase diagram of so-called calls and returns. So what you see here are calls at different call sites, right? So here we are calling into procedure C1, or this is call site C1 calling procedure 1. Here we have C2 and up to C4. And then here we are returning to return site 4. So this is matched, right? Then this return matches this call. Here we have another call that is then matched by this return, and so on and so forth. Okay, and we can also have repeating calls into the same procedure, but they must always be matched by the corresponding returns. Then the other thing is we can have other such staircase diagrams like you see down here. But there's one important rule that we can only descend as much as we have ascended, right? So basically it means when your call stack is empty, you obviously cannot return anymore, right? So in a regular Java program, for instance, you cannot return past the main method. That wouldn't really make any sense. And so that's another rule that has to apply to these diagrams. And also what I already said, right? So every descending step here must match a corresponding ascending step. Okay. Now that looks simple enough. If you have regular sequences of calls and returns, that gets a little more complex, but not much when you are thinking about recursion. Because in recursion, you can have the following situation, right? So let's say at the beginning, we have some entry into the recursion, right? So we have some location U, for instance, that is calling into a procedure P. And now we are at the start point of procedure P. And then P is somehow calling procedure I. So next we actually move into procedure I to its start point. And then Q can actually call another procedure J, which calls R, which calls K, which calls back into P. So we have some recursion. But then at some point, depending on a condition, for instance, it can also break the recursion by directly jumping to its exit of Q. Okay. And then the point is when you then in the end break the recursion, when you exit Q, you need to unroll all the recursive calls that previously happened, right? So definitely we need to go back to EI because we had SI before, and we also need to go back to EP because we had this call to P before. But depending on how many recursive descents we had here, we also need to unroll this loop here a corresponding number of times, right? And so these are basically the paths that you get, right? So we have a data flow function that initially computes until this point. Then we have a data flow function that describes these potential iterations that we had here. We have one that describes this flow. And then we have potentially a number of iterations backwards, like we see here. And then in the end, we have this dashed blue part, G prime, that describes the suffix of this data flow. And so a very simple instantiation, actually a minimal one, would be this one here, right, where you have F prime and then H and then G prime, and you have no recursive calls at all. But then you can have an arbitrary number of these recursive descents. And therefore, this graph structure basically describes a language of paths that are labeled this way, right? That describe all the possible data flows that you can have here. And for all of these paths, you can say that for a path from U to V, G must be applied exactly the same number of times as F. Okay, so these G's here must correspond to these F's. And also the prefix of the above path, for any such prefix, G can be applied only at most as many times as F, right? Because again, you cannot return more often than you did actually do the calls, right? And if you think about this, well, we're actually coming back to a stack, right? So the right data structure to do such matching and counting between these Fs and these Gs, it's a stack automaton. And basically you need some stack-based data structure to keep track of this one way or the other. And some of the algorithms we will be discussing, they will also be modeling the stack at least implicitly to some extent. Yeah, thinking about the staircase diagram, that's basically just getting back to what I explained to you, right? So we have these different procedures that are being called here, and you see these calls here on the left-hand side, and then we have a corresponding number of actually corresponding returns on the other side. Now, I just told you, in general, you cannot return from a procedure that you never called, okay? And so for almost all purposes, when you conduct a program analysis, you do not want to follow it along a return edge for which you do not have a corresponding call edge. But there's one important algorithmic exception, and that I briefly want to mention. But I will only do this briefly here because we're going to be talking about this in depth in my other course, DECA 2, in the next semester. So this exception are so-called demand-driven program analysis, which typically operate inside out. So a demand-driven analysis is one that tries to compute information not throughout the entire program, but only for certain, let's say, variables or program points that are of interest for which there is a demand. And now we can imagine that we have an analysis that tries to find data leaks from secret to this leak method here. But we want to do it in such a way that we do a bottom-up analysis, basically, or inside-out analysis. So we start at leak first and walk our way backwards to find whether whatever is leaked here is actually a secret. Okay, remember that I told you initially that taint analysis is an analysis that you can do in both directions. And here we're actually doing it in a backward way. But not only backward, but we're actually starting in a callee, right? So we're starting within foo, which is a procedure that is called by main. So we are starting the analysis in a callee procedure, and it might end up in a caller procedure here in procedure main. So that's our assumption here. But now if you look at this, if we start at leak, then, well, we actually do not have a corresponding call, right? So here, after processing leak, we would be returning from foo into main. So we have such a return here, but we have no corresponding call. And normally I would say, don't do this, right? Because it doesn't make sense. You have never seen a call. But here we deliberately want to do this because this analysis, it basically ignores, as a first step at least, everything that has happened up until this point in the program. And it's just searching its way backward from here. Now, what you need to do now is you need to actually look this is called an unbalanced return because you have a return without a call. And in these cases, the analysis has no chance but to return into all possible callers. Because here, looking at this execution of foo, we do not know where foo was called from, right? Because we don't know anything about any call site so far. So such an unbalanced demand-driven analysis would now basically consider that this call to foo could have come from here, or it could also have come from there. So you basically propagate this information here back to this call and to this call. And then only later, as the analysis works its way upwards here and also there, will it figure out that for this one call site here, it would actually find that the value originates from this secret method. And for the other call site here, that is not the case. Now you may wonder, why does that ever make sense? Why don't I just do a forward analysis and be done with it? There are cases where you can have many different sources and only a few select things that are interesting to you. And they might be deep down in some library or API. And we have had such cases in our research. And then such a setup makes sense because when you then do a backward analysis, you only have a few starting points to consider, and you can walk your way backwards from there. If you were to try it the other way around, you would have thousands of potential sources to start with, and that would make the analysis not very scalable. But that was just a fast forward. So for the remainder of this lecture this week, please consider that we don't have a demand-driven analysis, so we are always starting at the beginning of the program with our analysis, and therefore we are also not assuming that we could have any unbalanced returns. So in other words, for the remainder of this lecture, all the returns are going to be balanced. Getting back to this problem of context-sensitive analysis. So what I showed you so far was that we have this problem of unrealizable paths, right? So we need to distinguish different calling contexts. In particular, we want to make sure that we only return information to the right callee that could have actually, to the right caller, to the right calling context that could have actually made the call, right? A second question there is though, which calling context or which calls of a given procedure we actually want to distinguish. So in general, we want to analyze different callee procedures multiple times for different contexts so that we gain precision. But the question is, how do we do that? And which parts of contexts can be merged and which ones should be kept apart? That might sound a little abstract, so let me show you an example of this. Um, let's assume we are analyzing this little program here, and I will admit it's a very contrived program, but I want to keep it simple, and I just want to make the point that I'm trying to make. So let's assume we have this program. It's having some number here, 42. The value is not important. Apparently, it's supposed to be some secret key. Please don't do this. Please don't put numbers, constant numbers as secret keys in your program. But for the sake of the example, just assume we have that here. And now we can, first of all, assume that we are doing a taint analysis, okay? And for a taint analysis, if we analyze this procedure here, then first of all, we have this calling context C1 that I labeled here, so this call side. And at this calling context, performing a taint analysis here, we will see that, okay, we have a taint that propagates here, which propagates back to the return, and is propagated to the secret key. Okay, so the analysis might tell us at call site C1, foo, it returns a tainted value. Okay, because we assume this value to be tainted, so that will also be returning something that's tainted. Now, if I apply the same analysis to the second call site here, to C2, the second calling context, the analysis will also tell us, well, also here, foo returns a tainted value. So now you have two contexts that with respect to that particular analysis, with respect to taint analysis, they are equivalent. And in particular, this means that we can merge together the context information for these two different calls, right? So we don't really gain anything by keeping it apart. We can save memory, on the other hand, by merging these two contexts into one. And later on, we will see static analysis framework that exactly attempt to conduct such merging. Now, if we think about another analysis here, let's think about constant propagation. Things are a little bit different because now we are actually caring about this particular numeric value. And the analysis here would tell us that at context C1, foo returns the value 43, whereas at context C2, it returns the value 44. So with respect to that analysis, the contexts are different. And in order to get a precise analysis, you do want to distinguish these contexts. And that's an important message that I want to bring across. So there can be situations where you want to analyze the calling procedure multiple times in different contexts, because this difference between the two analysis passes matters. But there can be other situations where the difference doesn't matter, where, well, basically there is no difference, right? With respect to the analysis, you obtain the same information, and therefore no such distinction is necessary, right? So that's an important distinction to make. And in general, you can use different kinds of contexts that you choose to make this determination whether something should be distinguished or not. We will be seeing later on that there is a representation using call strings. So these basically encode methods or call sites on the current call stack within a string. And that can be used to distinguish different analysis passes of the same callee procedure that originate from different calls within different contexts. But then you can also use input domain values as contexts. These are then so-called value contexts. So here the idea is that you do not distinguish different analysis passes at different call sites, but you rather distinguish different analysis passes that have different abstract input values. And that can also make a lot of sense. And we'll be talking about that in depth as well. And you can even use information about the currently executing object as a context. That is then so-called object-sensitive analysis. So that's a special form of context-sensitive analysis, where you basically distinguish different analysis passes that occur with respect to different owner objects. So for instance, if you're analyzing the same procedure foo, but one times it's called on object O, and in the other case it's called on object P, and those two objects are different and they're distinct objects, then you would basically distinguish these different analysis passes. And this can make a lot of sense in general in object-oriented programming languages, because very often there certain procedures and the state that they alter are bound to the owning object. And there are empirical papers that shows that a certain level of object sensitivity at least is often beneficial. Now we will be talking more about this in depth in the upcoming weeks. So in fact, the next, I think 3 weeks or so will all be about different conceptual frameworks that have a variety of different trade-offs in this space. So they choose different context representations, which all have different pros and cons, and I'll be carefully explaining to you which of these different representations are useful in what setting. There are different algorithms that are better implemented in some of these frameworks rather than in others. And I think for you it's important to understand what that relationship is. Before I get there, this week I want to talk more about important language features that have some importance to interprocedural static analysis, and I'll be explaining that to you in the next video.